All right, so I just want to wrap up section 9.2 so we can practice some in class. All right, so geometric series. Recall that a geometric sequence is a sequence whose consecutive terms have a constant ratio, okay, a constant multiplier. So then a geometric series is the sum of those terms of the sequence. Notice that n is equal to 0 is where our series starts. And when n is equal to 0, if we plug that value in, we get our first term, which is a. Okay? Graphically, this would represent our y-intercept. All right, knowing that you have a geometric series, we have a lot of information that can be determined. So let's start with the divergence of a geometric series. A geometric series diverges if the absolute value of the ratio is greater than or equal to 1. So if our multiplier is bigger than or equal to 1, the series automatically diverges. So the series converges if the absolute value of the ratio is between 0 and 1. So we can have negative ratios to determine convergence or divergence. We just look at the absolute value of those. If the series converges, it converges to the sum a divided by 1 minus r. Okay, where a is our initial term, a is our first term, initial value, whatever, and r is our ratio. Okay, and that will always occur when the absolute value of our ratio is between 0 and 1. And we'll put this to use in class tomorrow. The last topic in 9.2, which is very useful, is the nth term test for divergence. Okay, so let's start with the theorem first. If a series converges, then the limit of the nth term of the sequence will be 0. Okay, so we looked at this series yesterday. We said here's this series, 1 over 2 to the n. We listed the terms, we looked at the partial sums, and we said the partial sum was 2 to the n minus 1 all over 2 to the n. Okay, we found the limit, and we found the sum of this infinite series was 1. Because the sum existed, the series converges. Okay, so using this theorem, because we have a convergent series, if I were to look at the limit as n approaches infinity of the nth term, so remember that this is a sub n, then this limit needs to be 0. And we showed that as part of an example as well. What's very important for this, the converse of this theorem is not necessarily true. So if the limit of the nth term of a sequence is 0, then we cannot necessarily imply that the series will converge. Okay, so the converse of this is not necessarily true. All right, so if P, then Q. That's our conditional statement. If a series converges, then the limit of the nth term must be 0. The converse of this, if Q, then P, not necessarily true. The contrapositive, however, so if not Q, then not P, this is an important theorem that we'll use repeatedly. So the second part to this, the contrapositive, if not Q, then not P. So if the limit of the nth term of a sequence is not 0, then we can automatically know that the series diverges. So if the limit is not 0, then the series diverges. Okay, so let's look at 3 quick examples. A sub n, okay? The limit as n approaches infinity of 2 to the n, well, this limit does not exist. This limit approaches infinity. So since this limit does not equal 0, we can conclude that the series diverges. Now, what you'll find throughout the course of this chapter is we can use a couple different tests to show for convergence or divergence. So if I look at this, I know that this is a geometric series with a ratio of 2. So automatically, I know that the series diverges as well. Okay, because geometric series only converge when the absolute value of the ratio is between 0 and 1. So 2 different ways to prove the same thing. The series diverges. Okay, limit as n approaches infinity of a sub n. This limit approaches a half. Since the limit of the nth term is not 0, we can conclude that the series diverges. So no additional work is needed. If the question asks for convergence or divergence of the series, this is our nth term test. It only shows divergence, however. And you'll see that on the next one. Okay? Limit as n approaches infinity of 1 over n is equal to 0. Okay? So what does this mean? This means the nth term test does not apply. So that's what we'll be working on further. What are some other tests that we can use to prove convergence or divergence of a series? Okay? So theorem does not apply. And what does that mean? We don't know. Okay? No conclusions can be made using this test about the convergence or divergence of the series. Okay, see you in class.